Good morning. A warm welcome to lecture 3rd of unit 1, and in this lecture we will be talking about Gram-Schmidt orthogonalization procedure. But before that, let us recap what we have learned in the first week. So, we have introduced the big idea of L2 space or L2 waveforms or L2 signals, and we have said that the class of all finite energy signal belongs to L2 space. So, we know that the energy of the signal can be computed by the integration of mod square of that function, and if this quantity is finite, we say that the signal has finite energy, and if the signal has finite energy, the signal is an L2 signal. Now, we love these L2 signals because L2 waveforms are vectors, and L2 waveforms always have Fourier series and Fourier transforms representation. So, this is the one big idea that we have learned. Second, we have learned about the inner product. So, inner product is same as the dot product. So, in case of vectors we love this dot product, in case of signals we do this inner product. What is inner product? If you want to compute the inner product of the two signals, you have to multiply the signal with a conjugate of another signal, and then you have to integrate it from minus infinity to plus infinity, and this is the inner product of the two signals. Physically, the dot product and inner product has the same meaning. Okay. In case of vectors, we can compute the norm of a vector. Norm of a vector is also the length of the vector, and this could be obtained by square root of dot product of the vector with itself. In case of signals, we can also compute the norm of a signal by the square root of inner product of the signal with itself. This quantity is nothing but is the energy of the signal, and hence norm of the signal is nothing but it is the square root of energy of the signal. So, we can learn that length of the signal is nothing but square root of energy of that signal. Okay. Carrying this idea forward, we can talk about the angle between the two vectors, and you must have learned this identity before, that cos of the angle between two vectors is given by the inner product of the two vectors divided by the length of the vectors. Okay. In case of signals, the picture remains exactly same. If you want to talk about the angle between the two signals, then you can use the same identity, that is the cos of angle between the two signals is given by the inner product of the two signals. So, here we are computing the inner product of the two signals divided by the length of the signals. Remember, this is the length of the signal because it is the square root of energy of the signals. In case of vectors, we learned about Cauchy-Schwarz inequality, and Cauchy-Schwarz inequality can be easily derived from this expression, and it states that mod of the inner product of the two vectors is less than or equals to the product of the length of the vectors. In case of signals, exactly same thing follows, that is the mod of the inner product of the two signals is less than or equals to the product of the length of the signals. Now, using this analogy between signals and vectors, we have easily derived this inequality, otherwise it would have given us tough time. So, that is why we love this analogy between signals and vectors, things becomes trivial and easy. Okay. Let us take this case forward and let us define what are known as orthogonal signals. In case of vectors, if you want to talk about the vectors, if the inner product of two vectors is 0, then we say those vectors as orthogonal vectors or perpendicular vectors. In case of signals, again if the inner product of the two signals is 0, we call those two signals as orthogonal signals. In case of vectors, we have unit vectors have the magnitude of 1. In case of signals, we have these orthonormal functions or orthonormal signals. Orthonormal functions or signals are first orthogonal functions and signals, and secondly they should also have the unit energy. So, if the signals are orthogonal and they have unit energy, then we call those signals as orthonormal signals, orthonormal functions or orthonormal waveforms. Okay. So, these are the three important ideas that we have learned in the last week. So, we have also seen about the orthogonal expansion of a signal. So, to think about this orthogonal expansion, it is easier to think it in terms of vectors, and again it is easier to think it in terms of a 3D vector. So, if I have a 3D vector can be understood as it is built using components in the x, y and z direction. Similarly, in the case of a signal can be considered as if it is built using orthogonal or orthonormal functions. So, these x and t's are orthogonal or orthonormal functions. Okay, so far so good. Again, if we want to think about how big is the component of this vector r in the x direction, you can simply obtain this by dotting this vector r with the unit vector in the x direction. In the case of signals, if we want to find out the component of the projection of x t in the direction of reference signal x and t, you can simply obtain this by taking the inner product of the signal with the reference orthogonal or orthonormal function x and t and dividing by the energy of that orthogonal or orthonormal function. Of course, if this is orthonormal function, then this quantity is going to be 1. So, we can understand about this orthogonal expansion by using the analogies between vectors and signals. Okay. And if we make use of this analogy, then this is really simple and it is like a 5-finger problem. And let us do a question based on this. So, I have the two signals x t and y t, and what I am interested in here is finding out the angle between the two signals. Now, we have learned that if I am interested in finding the angle between two signals, I can use this identity where I need to take the inner product of the signals involved. If they are real, I do not have to take this conjugate, and I have to divide it by the square root of energy of these two signals. So, what I need to do is I need to find out the inner product of the two signals involved and the energies of these signals involved. So, let us try to do this. So, first let us derive what is the energy of signal x t, and this can simply be obtained by carrying out this integration. And this will turn out to be 2. Similarly, I can find the energy of the signal y t, and this will also be 2. Then what I need to find out is the inner product between these two signals. So, if I want to find the inner product between the two signals, I can break this integration in certain regions. So, first I am considering the area of this product of these two signals in the limit going from 0 to 0.5, and then this product is 1. Then I can consider the integration from 0.5 to 1, where the product is -1, and then I can go from 1 to 2, where the product is 1. So, I will get 1. So, cos of angle between x t and y t will turn out to be 1 divided by 2. So, angle will come out to be cos inverse of half, which is 60 degree. So, using some simple ideas, we have been able to talk about the angle between the two signals. Okay. Let us now move on to the main theme of today's lecture, and in today's lecture we will learn about Gram-Schmidt orthogonalization procedure, and then we will see the transmitter and receiver structure. Okay. So, let us get started with this Gram-Schmidt orthogonalization procedure. So, what is the objective of this orthogonalization procedure? So, the idea is, let us assume that we have m energy signals. So, this is important, we have m energy signals, that means the energy of these signals is finite, and we want to find n basis functions for the signal space representation of these m energy signals. That means, I want to convert these signals into vectors, and I want to think about these signals in terms of basis functions, and the number of basis functions that I have is n, and we will find out that this n is always less than or equals to m. So, this is the objective. Let us get started with it and see how we do this orthogonalization procedure. So, the first idea is, let us start by picking a signal. I could have chosen any signal to start with, but let us start with this signal S1t. So, I have started with this signal S1t. Remember, these basis functions that we will obtain will not be unique basis functions, but they will depend upon the order in which you do this orthogonalization. So, because we have started with S1t, we might get a different answer than what we would have got if we would have started with another signal SMT. So, it really depends upon the order in which you are carrying out this orthogonalization procedure, the basis functions might be different. However, the dimensionality, that means how many basis functions we need for the signal space representation, would not change. It would be invariant to the order in which we are carrying out this orthogonalization procedure. So, dimensionality is invariant to the order, and also the inner product between the two signals would also be independent of the order in which you carry out this orthogonalization procedure. And this is really what is important, the dimensionality and the inner product between the two signals should remain invariant. Okay. So, let us get started. So, we have started by choosing the signal S1t, and we are trying to find out the first basis function, and we have said the first basis function is nothing but S1t divided by root of energy of signal S1t. So, E1 is the energy of S1t. Why we have divided it with the root of energy of signal S1t? Because we want this basis function to be an orthonormal basis function, and for orthonormal basis function the energy of phi 1 t should be 1. So, let us see what is the energy of phi 1 t. Energy of phi 1 t can be obtained by carrying out this integration. We do not have mod in here because we are assuming that everything is real in this case. So, all signals are real and the basis functions are also real. So, when we compute the energy of phi 1 t, you can simply plug in this value in this integration. So, as we have done here, and what you have in the numerator is the energy of S1 t. So, we have E1 in the numerator, in the denominator also we have E1. So, the energy of phi 1 t turns out to be unity or 1. Hence, the first thing is clear that this phi 1 t basis function has a unit energy. S1 t can then be thought as given by this quantity, where we are just taking this to this side. Okay. So, we have obtained S1 t in terms of phi 1 t, or rather phi 1 t in terms of S1 t. Let us move on and let us try to obtain phi 2 t. but before finding out phi to t, let us understand this expression. So, what is the meaning of these terms S to 2 and S to 1? So, S to 2 is the projection of S to t on phi to t. So, S to t on phi to t, that explains this numbers, these numbers 2 2. S to 1 will be projection of S to t on phi 1 t. Okay. So, this explains this subscript. Okay. So, what do we mean with this after having understood the nomenclature? So, let us consider two vectors first. So, if I have a vector S 2 and a vector S 1, and let us assume that I have considered a unit vector in the direction of S 1, and then there is a unit vector which is perpendicular to u 1, and we have already learned in one of the previous lectures that if you have a vector, you can decompose this vector in terms of a parallel components. So, let me assume that I have a parallel component to vector u 1 and I have a perpendicular component to vector u 1. So, this I say that maybe I have some constant times vector u 1 and I have some constant times vector u 2, because vector u 2 is perpendicular to vector u 1. So, I can think about a vector decomposition in terms of two unit vectors, where these two unit vectors are perpendicular to each other, and what remains is finding out these coefficients C and D. If you want to find C, it is quite straightforward. C can be obtained by dotting S 2 with u 1, and D could be obtained by dotting S 2 with u 2. So, these vector operations are trivial, easy, and we are using the same ideas, but for the case of signals. So, I am saying that a signal can be decomposed in terms of two orthonormal functions, and S to 2 and S to 1 gives me the projection of S to t along those orthogonal or orthonormal functions. Okay. So, let us, after having understood this basic idea of how we are writing out this expression, let us try now to find out phi to t. So, phi to t can be simply obtained by using this relationship. I am doing some algebraic manipulation, and from this relationship I can easily think about what this phi to t may be. So, let us see if we have all the knowledge available to construct this phi to t. So, in this equation we already know S to t, because it must be given. We already have learned what is this phi 1 t. Phi 1 t we have obtained in terms of S 1 t. S to 1 is also known. If S to t is known and phi 1 t is known, S to 1 is also trivially calculated by taking the inner product of S to t with phi 1 t. This is a straightforward thing. What is unknown is this S to 2. Now, if you look at this S to 2, S to 2 is also a function of phi to t, and hence there is a chicken and egg problem. Until and unless we know S to 2, we cannot find phi to t, and until and unless we know phi to t, we cannot find S to 2, and hence we carry out this orthogonalization procedure in a slightly different way. So, instead of directly finding phi to t, what we can do is we can define an intermediate function g to t, which is defined like this. So, g to t is nothing but it is the difference of s to t with s to 1 and phi 1 t. Okay. Now, let us first check whether this function g to t is it orthogonal, is g to t perpendicular or orthogonal to phi 1 t. Let us check this out. And how do we check this out? We can check this out by finding out the inner product of g to t with phi 1 t, and if that inner product turns out to be 0, we will be sure that g to t is perpendicular to phi 1 t. Okay. So, let us work this out. So, we are trying to compute the inner product of g to t with phi 1 t. So, here we can plug in the value of g to t, which is this, multiply this with phi 1 t, again there are no conjugate and things like that because everything is real, and then we can work out this integration. So, taking this phi 1 t here, we get this integration, and then multiplying this phi 1 t with this part, we get this expression. And now, by definition, this quantity is s to 1, and if we look at this, s to 1 is constant. So, it could be pulled out of this integration. So, what we will have is, and because this phi 1 t is orthonormal, its energy will be 1. So, this quantity is 1, this quantity is 1. So, what we will have is s to 1 minus s to 1, and this we are saying is 1. So, essentially what we have is s to 1 minus s to 1, and this is 0. Okay. So, we have proved that g to t is perpendicular or orthogonal to phi 1 t. Okay. So, now after having understood that g to t is perpendicular to phi 1 t because its inner product is 0, we can quickly define phi 2 t as g to t divided by the length of g to t, and length of a function is the square root of energy of that function. So, this is what we are doing. We have this g to t and we divide by the square root of energy of g to t. If we do this, then we know for sure that phi 2 t has a unit energy and it is an orthonormal function, and this is what we want, and that is why we are doing this scaling operation. Let us find what is the energy of g to t. Energy of g to t could simply be obtained by finding out the integration of a square of g to t. So, plugging in the value of g to t here, then using the identity a minus b whole square as a square plus b square minus 2 a b. So, this quantity we know is E 2. E 2 stands for the energy of the second signal in consideration. We already know how to work this integration out. This, even by look, you should be able to tell that this should be nothing but s squared to 1, and this expression. So, let me work this out here. So, this is 2 s to 1 s to t phi 1 t dt, and you know that this is s to 1 by definition. So, we have this will turn out to be minus 2 s squared to 1. So, finally, we have 1 s squared t 1 with plus, and we will have 2 with minus. So, finally, we will have 1 remaining with a minus. So, this is the energy of g to t. So, finally, we can say that phi to t is nothing but g to t divided by the square root of E 2 minus s square to 1. Okay, so, we have obtained phi to t, and similarly we can carry out this orthogonalization procedure and we can obtain other orthonormal functions as well. Let me just do one more. So, we can start by computing phi 3 t, and phi 3 t can be conveniently obtained as G3T divided by the square root of energy of G3T. And what is this G3T? G3T can be simply obtained if you subtract from the third signal. So, let us assume my third signal is S3T, and if I subtract from this S3T the projections of this S3T in the direction of phi 1 t and phi 2 t, then G3T would be given by this. So, what we are doing here? We have got this S3T, and this is the projection of S3T along the reference direction phi 1 t, and this is the projection of S3T along the reference direction phi 2 t. We subtract from this S3T these terms, and what is remaining is G3T. Now, it should be clear from inspection that this G3T will be perpendicular to phi 1 t and it will be perpendicular to phi 2 t. Why is this? Because we have already subtracted from S3T whatever projection it had along phi 1 t and phi 2 t. That means, there should not be any energy left in S3T along phi 1 t and phi 2 t direction, and hence the inner product of G3T with phi 1 t should be 0 and inner product of G3T with phi 2 t should also be 0. You can work out the proof yourself. Here we are just presenting the intuitive idea behind why should this G3T be perpendicular to phi 1 t and phi 2 t. And we can generalize this procedure. You can obtain first a GIT. GIT would nothing be, but you have to subtract from the ith signal the projections of this ith signal on all previous basis functions, and from this GIT you can obtain this phi I t by just having in numerator this GIT and then dividing it with the proper scaling factor, and the proper scaling factor is nothing but it is the square root of energy of GIT. And as we have worked out, this expression is also same as this quantity. So, using this idea of orthogonalization, you can obtain various basis functions for the orthogonal expansion of a signal. The basis functions that we have calculated are orthonormal basis functions. Okay. So, let us make this more concrete with one example. So, let us consider here the two signals S1t and S2t, and let us assume that these two signals are given as here, and we want to find the right signal space representation for these two signals. Okay. So, let us start by defining phi 1 t. So, phi 1 t can be easily obtained by having S1t and dividing it with the square root of energy of S1t, or rather dividing it by the length of S1t. Now, so the first step is that how do we calculate this energy? Energy can be simply obtained by taking the inner product of the signal with itself, and you know that instead of running out this integration from minus infinity to plus infinity, you can simply run this integration between 0 to t by 3, because everywhere else the product would be 0, and in this limit the product would be 1. So, we can easily obtain energy of S1t as t by 3. Okay, good. So, once this energy is known, we can easily obtain this phi 1 t. Phi 1 t would be nothing but this S1 t divided by the proper scaling factor, and the scaling factor is root of energy. So, we have to take the root here. So, S1 t divided by root of t into root of 3 like this. So, phi 1 t is nothing but this quantity, and we can also draw this. So, if S 1 t is known, then phi 1 t is exactly the same thing, only the magnitude changes, and instead of 1 it becomes root 3 by t. So, this is phi 1 t. Okay. So, this is phi 1 t as we have also drawn. The answer is correct. Let us now go to the second step in finding what is this phi 2 t. So, once we know this S 2 t and phi 1 t, we can first obtain this S 2 1. S 2 1, remember, is nothing but it is the projection of this S 2 t on phi 1 t. So, I have to find out this integration. Finding out this integration is rather trivial. So, you can work it out yourself and find out that the value of S 2 1 is nothing but it is the root of t by 3. Now, we can also find out the signal S 2 1 into phi 1 t. So, what happens is that you just have to multiply this phi 1 t with S 2 1. S 2 1 is this quantity. So, you have to multiply this thing with root of t by 3. So, it becomes 1. So, this is S 2 1 times phi 1 t, and thus you can easily obtain G 2 t, which is nothing but it is the difference between these two signals. S 2 t is already known, S 2 1 phi 1 t we have already obtained. If we take the difference between these two signals, G 2 t can simply be obtained like this. So, finding G 2 t is easy. If we know G 2 t, we can find phi 2 t by having this G 2 t and dividing it with the length of G 2 t. Length of G 2 t again is nothing but the root of energy of G 2 t, which you can simply obtain by carrying out what is the energy of this signal and what is the root of that. You can simply obtain that this is again root of t by 3. So, phi 2 t is nothing but this signal. So, same as G 2 t, only we need to change the amplitude. Okay. So, it is easy, simple. Now, what remains is we have yet to find out this S 2 2, but that should also be trivial because we have been able to find out phi 2 t, and S 2 2 is nothing but it is the projection of S 2 t in the direction of phi 2 t. So, let us see. Let us first see what is S 2 1. We have already found out that this is given by this expression. So, I can write this S 2 t is nothing but this plus S 2 2 phi 2 t, and S 2 2 again can be simply obtained by carrying out this integration. Again it is trivial and I leave it to you to do this, and again it comes out with the same form that this is root of t by 3. So, finally, the expression for S 2 t is this expression. Let us now try to wind up this issue. So, we started with S 1 t and S 2 t. We easily derived the expressions for phi 1 t and phi 2 t, and we have said S 1 t is this and S 2 t is this. Now, very conveniently we can draw the signal space representation of these two signals. So, we can assume that we have two vectors phi 1 t and phi 2 t. These vectors are perpendicular vectors, they are orthonormal vectors. So, they have to be orthogonal. So, they have to be perpendicular, and these vectors comes out with unit energy, right, and S 1 t is this vector. So, see that this only has a component of phi 1 t, and this has got this value along phi 1 t. So, I have to consider a point along phi 1 t with this value, and S 2 t contains both phi 1 t and phi 2 t, and it has the value along phi 1 t of root t by 3 and also along phi 2 t of root t by 3. So, this is this vector. Now, what you can see very clearly from here is that now we can talk about the angle between these two vectors, and you can easily obtain the distance between these two vectors. So, we have been able to convert the signals into our vector space, and this is the idea of signal space representation. If I would have had more signals, again nothing changes. Conceptually, you just have to do more algebra and you can convert the set of m signals into a convenient vector space or signal space representation. Okay. Now, let us move to this transmitter and receiver structure. Why do we want to do this already is because it makes use of the ideas that we have just developed while going through this signal space. So, the transmitter and receiver structure follows directly from the ideas of signal space. We want to maximize what we have learned, and thus it is a good idea to introduce this already. The second important point that you can note is when we confront ourselves with noise and other non-idealities, these will not change the receiver and transmitter architectures or structures. So, they will remain same. So, it is a good idea to think about these transmitters and receiver structures already from today, because they form the substratum of what is digital communication. Okay. So, let us proceed by first looking into the transmitter design. So, transmitter design solves a simple problem. It converts these sequences to waveforms. Okay. So, we have a sequence, and as I have already said, a sequence can be understood as a bunch of numbers. So, I have a bunch of numbers here. These numbers can be real numbers, or these numbers can be quantized real numbers. We call these quantized real numbers as symbols. Okay. So, I take in a number, and let us first focus on what the subscripts of this number denote. So, here I denotes that this is a sequence corresponding to signal SIT, and 1 denotes that is the first number of the sequence. Okay. So, I have this number SI1, I multiply this number with phi 1 t, and what I get here is SI1 times phi 1 t. Okay. So, at the output of these multipliers, I will be going to get similar products, and this summer collects all such products, and we get SIT. So, what is SIT? SIT would be nothing but it would be sum of these products where j spans from 1 to n. And this is exactly what we have said, that if we want to think about a waveform is nothing but it is a linear combination of orthonormal functions. And what are these phi 1 t and phi 2 t and phi n t? They are nothing but these are the orthonormal functions. Okay. So, what is the transmitter design? It looks very simple, isn't it? So, you have a bunch of numbers, you multiply these bunch of numbers with orthonormal functions, you collect all products by using a summer, and you get to a waveform. So, this is as easy as it can get. Okay. Let us now move to the receiver design. So, in the receiver solves the problem of converting a waveform into a sequence. So, I have a waveform which I call as RIT. Okay. I pass this waveform through a multiplier. Again, this multiplier is fed with orthonormal function phi 1 t. So, at the output of the multiplier, I am going to have RIT times phi 1 t, and then I pass it through an integrator which integrates this product from minus infinity to plus infinity, and what I get is this. And I already know this. What is this? This is the inner product of RIT with phi 1 t, and I know what this gives me. It gives me the coefficient of projection of RIT on phi 1 t, and I call this as R I 1. Okay. Of course, as the energy of this orthonormal function is 1, I do not have anything in denominator, or I have 1 in my denominator. So, what I get is R I 1, which is the coefficient of projection of R I t on phi 1 t. Okay. Similarly, I can pass this R I t through other orthonormal functions, and I can get the coefficients of projections of this R I t on other orthonormal functions. In this way, what I get is a sequence, and here the numbers in the sequence corresponds to the projection of R I t or the received waveform on various orthonormal functions. So, again in this way, using the simple design, I can convert a received waveform to a sequence. Okay. Let us now look something more on this slide. This block, which consists of a multiplier and integrator, is known as a correlator. So, this is a correlator, and hence in the receiver we have bunch of correlators, or we have a bank of correlators. Okay. Let us now try to look into what is this matched filter. So, matched filter is same thing as correlator, however, from practical point of view its implementation is different. So, correlator has a multiplier and has an integrator. On the other hand, a matched filter has a filter, a linear time invariant filter, and a sampler. Okay. So, let us see what is the result or output of this block. So, suppose I have a matched filter which has an impulse response like this. Let us try to investigate what is the output of this system. Okay. So, let us first concentrate on the output y t at this point. So, y t can be given by convolution of input with impulse response, which you must know is this. So, this is the y t output of this filter, which is obtained simply by carrying out the convolution operation between the received waveform and impulse response of the filter. Now, we know that h of t is this. So, h of t minus tau should be so what we do is, instead of t we replace this t with t minus tau. Okay. So, I have already done this. Let us look at this. As I have said, y t is obtained by the convolution of the received waveform with impulse response of the filter, and because I already know that the impulse response of the filter takes in this form, what I can do is I can substitute this value of impulse response in here. I get this. I can solve this out and I can get an expression of y t. Okay. Now, we have calculated y t, and the idea is, suppose I sample this y t at capital T, I get R I 1. This is what I claim, and let us see if this is true. Okay. So, I want to look this y t only at the time instance where t is same as capital T. So, let us look at it. So, when t small t is same as capital T, this should become capital T, and what we will get is this thing. Okay. So, if t becomes capital T, this becomes 0, and what I have is R I tau into phi 1 tau d tau, and this we know is nothing but it is the inner product of this received waveform with this orthonormal function phi 1 t, and I have said it already that this gives me the projection of, or this gives me the coefficient of projection of R I t on phi 1 t, and this coefficient of projection is nothing but R I 1. So, what we have got is that this system has the same output as this system, and hence matched filter gives me exactly what a correlator gives. Okay. So, matched filter theoretically is same thing as the correlator. Let us now substitute these systems in the full blown receiver. So, now we know that in a receiver you have these bunch of correlators. Each correlator chooses a multiplier where the one of the multiplying factor is the orthonormal function. In the case of the mesh filter, we choose various filters and samplers, and the impulse response of these filters is matched to the orthonormal functions. Okay. So, the question is, which one should we prefer? Accurate analog multipliers are hard to build, and that is why this meshed filter design was preferred. It is easier to make filters rather than accurate analog multipliers. But for this mesh filter, there is a issue of physical realizability of the system. So, you must have learned in the course in signals and systems that we can only realize systems which are causal systems. Causal systems means the systems which are non-anticipatory systems. That means these are the systems which cannot anticipate an input. Okay. So, if you want to realize a system, it will definitely be a causal system. It will not be able to anticipate which input is going to come in future, and such a system is known as causal system. One property of a causal system is that the impulse response of that causal system is 0 for time t less than 0. And why is this? Because if a system is causal system, it can only have the response to an impulse after an impulse is applied. Impulse response is the response of the system to an impulse. So, if a system is causal, it can only respond to an impulse after an impulse is applied. An impulse is applied at t equals to 0. Impulse signal is a signal which exists or has its effects at around t equals to 0. So, the response of the system can only come after t equals to 0, whatever that response is. It cannot proceed before an impulse is applied, because it is a causal system, it is non-anticipatory system. So, the impulse response of a causal system is 0 for time t less than 0, and this is also the condition for the physical realizability of a system. Okay. Now, we know what is the impulse response of the filter. Impulse response of the filter was of this form. Okay. This implies that this phi t minus t should be 0 for t less than 0, because that is the condition for the system to be a causal system. Now, if we substitute tau as t minus t, t less than 0 implies that tau is greater than t. So, one way in which I can write this expression is that this condition translates to the condition that phi of tau should be 0 for tau greater than t. That means you can only have orthonormal functions which live for a duration of t. So, it cannot lie from minus infinity to plus infinity. So, the physical realizability of mesh filter puts some restrictions on the kind of orthonormal functions that this system can deal with. Okay, let us move ahead and let us see now the complete full blown receiver implementation. Maybe it is too far fetched because we have not yet studied noise and so on and so forth, but let us see how the full blown receiver looks like, and we will refine this when we study detection and other things. So, the first part of the receiver is take in this received waveform and produce a sequence corresponding to that received waveform, and then these sequences goes to this weighting matrix. Weighting matrix computes the inner product between this sequence, the received sequence, and the sequence available from the signal set. So, remember, receiver knows the signal set, receiver knows the sequences corresponding to that signal set. So, this weighting matrix just compute the inner product between this received sequence and the sequence of the signal set. Of course, we are assuming everything to be real in this case. So, there are no conjugates and so on and so forth. Now, there is a mental exercise that you can do and think about that this operation wherein you are computing the inner product between the sequences is same thing as the operation where you calculate the inner product between the waveforms. That means, if I take the inner product between the two waveforms, this inner product is the same thing as inner product between the corresponding sequences. Okay. So, this is a simple exercise and I request you to do it yourself. Okay. So, what this weighting matrix actually gives me, it gives me the inner product of the received waveform with all signals, okay, assuming that there are amp signals involved here. Now, based on these output, receiver selects the possible transmitted signal. So, it decides in the favor of the signal which has the largest output for this operation. Namely, for example, if r dot S1 is largest out of all these inner product operations, then the receiver selects S1 as the possible transmitted signal. Okay. So, this happens in the receiver implementation. It receives a waveform and from that received waveform it has to decide for the possible transmitted signal, and this is what it does. Now, I have little bit simplified this picture, and this picture will be true if I assume that all these signals happen with equal probability and these signals have equal energy. If this is not the case, then what we need to do is we need to add a bias here, and based on these outputs then the decision happens. So, this bias takes care if these signals are not equiprobable signals or these signals comes up with different energies, then this bias takes care of that. So, how to choose this bias and why we are choosing this bias, all these things will become clear when we do detection. At this point it is important and to appreciate that the decision that happens in a receiver is basically motivated by a bunch of inner product operations. Okay. One another issue, of course, you can have implemented this receiver in a slightly different way. So, in the previous case we had these matched filters and these matched filters had the impulse response which were matched to orthonormal functions. In this case what we are doing is we are matching the impulse response directly to the signals, and once you do this what you would see is this would directly give me the inner product between the received waveform and the signals. Okay. Now, once I directly get these inner products, what you can appreciate is that there is no requirement of this weighting matrix, and hence this architecture looks simpler. So, the question is which one should I prefer, and the answer is simple, because mostly m is larger than n and in most cases it is much larger than n, then in this case the number of filters that are required would be much larger than the number of filters that are required in this case. Okay. Number of filters, remember here that are required is n and number of filters that are required in this case is m, and because m is larger and typically much larger than n, this architecture would require more number of filters than this architecture, and hence this is a preferred design in most cases. Of course, here as well what we need to do is we have to add bias if the signals are not of equal energy and they do not occur with equal probability before taking the decision. Okay. So, with this we have come to the conclusions of today's lecture. In this lecture we have studied about Gram-Schmidt orthogonalization, we have studied about transmitter design, and we have looked into the receiver design as well, and we have looked into two important receiver designs. One design we refer to as correlator and the another designing architecture is referred to as matched filter. So, in the next lecture we will start thinking about other ways in which we can expand our signal. Thank you.